This is the final lecture we have in chapter 2 to bonding in solids in our course of solid state physics, and it's called as the van der Waals bonding. So as the name suggests, we will cover the basics regarding this type of forces, and as we will see, these are very weak forces and they are not visible unless we have the other forces basically negligible and zero in the case. So only in special cases the van der Waals forces start playing a major role in bond formation. And the van der Waals forces in general, I guess one could say that it's a kind of a family of different types of forces, and the associated bonding that forms van der Waals solids, it's slightly different from other bonding types that we have covered right now up until this point. First of all, it's very weak. So in terms of the bonding energies, we're speaking of only a few milli-electron volts per atom, and this is very, very little. So it's even weaker, these forces, than the hydrogen bond. And this means that we can only, in essence, see this force in place to play a role in solid formation when the other forces are small, negligible. So and when this happens, is that, for example, like we don't have the elements, they don't want to share electrons, and they don't want to receive electrons, so that when their valence orbitals are filled with electrons, that these forces start playing a role. And this happens when we have noble gases and the associated solids. So when we take a noble gas element and then we form a solid, then we will have a van der Waals crystal. And these van der Waals crystals, they really exist only at the very lowest of temperatures. And this is due to the fact that the bonding energies are so low. So if we just think about the equipartition theorem that says to us that the energy, the thermal energy that we have in the system is spread evenly with the different energy states, and that then dictates like the phase of our matter. Is it in solid form or in liquid form? And if we recall that a single 1 Kelvin of a temperature means roughly of 8.6 electron volts, 10 to the power of minus 5 electron volts, so that we see that the like few milli-electron volt bonding strengths necessitates the fact that we must really be in the lowest of possible temperatures, so at really like cryogenic temperatures, few kelvins. And let's go through some useful rules of thumb. Like I think a physicist should remember them. These are very useful at times. Sometimes they are not, but when they are super useful and they provide very useful intuition. So I recommend you memorizing these things. So when we are at room temperature, that's roughly 300 kelvins. This 300 Kelvin corresponds to an energy of 26 milli-electron volt. So kBT, Boltzmann constant times temperature, equals this energy. And you can also calculate it with the 8.6 times 10 to the power of minus 5 eV, and you get the same number. But this is a good rule of thumb. So please memorize this. At room temperature, 300 kelvins, 26 milli-electron volts. And then when we go to 1/10 of room temperature, and I can do the math, that's 30 kelvins. And then I can still do the math, that's then 2.5 milli-electron volts in terms of the temperature, in terms of energy, kBT. And if we have a kind of binding energies that are of the order of milli-electron volts, we see that in fact, for a van der Waals crystal to form, we need to go even temperatures that are less than 30 kelvins. And this is then quite a bit of a requirement from the cryostat that we have, so that you cannot like reach these temperatures with the kind of traditional cryostats anymore. So it's not, we see these van der Waals crystals in everyday life. That's what I wanted to say here. And then the final slide is that these van der Waals forces, they can be said that they are quantum mechanical in the sense that the bonding energies that we would have and this is the few milli electron volts per atom case. So the van der Waals bonding energies, they tend to zero, so they go to zero when the H bar goes to zero. So when the reduced Planck constant goes to zero, the binding energies go to zero. And of course, this means then that if we would be in a different universe and the Planck constant would be different, then also the van der Waals forces should be different. So, interesting. So if we are in a multiverse, my other multi-person might be feeling a different van der Waals forces. And these arise from quantum zero-point fluctuations. So this is what is being said. And of course, I'm a classical guy, so in classical sense, of course, also the temperature fluctuation in our system should also induce these things. But usually quantum mechanic people and the solid state physicists, they say that this is purely a quantum mechanical effect and no classical physics plays a role. But I'm a classical guy, and I would then start saying, but okay, what about like statistical electrodynamics, stochastic electrodynamics, that we do have fluctuations in the fields, and subsequently similar kind of forces should take place. But that's an argument between different physicists. So what happens and what gives rise to van der Waals bonding and forces is that we start having dipole-dipole interactions in our system. And these interactions then change the energy of the system. And then we have, again, the total energy of the system gets minimized when a solid form is being reached. So this is the kind of process that takes place in van der Waals solids. And what happens is that basically this whole process exemplifies, yet again, the kind of general trend and kind of general requirements that we have for a solid to form. So basically, in one sentence, we can wrap up what we have learned during this chapter 2. So a condensation from a liquid or gaseous state into a solid form takes place when the whole system minimizes its energy by forming a solid, period. That's the thing. So condensation results from minimization of energy. So that's in a way the only thing you need to remember to appreciate how and why solids are being formed. And with this principle in mind, if you can just calculate the total energy of your system, then you can calculate, in principle, start predicting how the system behaves, how solids are being formed, and how easily they still remain in solid form. And this is the last lecture we have on this chapter 2. I thank you for listening, and next we will be progressing towards the mechanical properties of solids. So please stay tuned, and I hope you enjoyed the ride this time. Thanks and bye-bye.